Good morning, students.
Good morning.
I welcome you all to day 4 of the series. Today we are going to be considering fields. There are 5 fields. We're going to be considering basically 3 fields, but some are, related to another. So they give rise to separate fields. So we have the gravitational field is what we're taking first, followed by the electric field, then followed by the magnetic field, then the electromagnetic field, and the simple AC circuit. Are you with me? All right. So let's go on to the gravitational field. Now, the gravitational field is any region in space around the Earth where the force of gravity can be felt. First, a field generally is a region in space where the effect or the influence of a force can be felt. So, for example, if it's magnetic field, it will mean any region around space where you can feel magnetic force. Am I clear? So that's what a field is. The forces are divided into 2. Basically, you have the what? The contact force, right? And the what? Non-contact or field force. So these forces are the non-contact or field forces. So, for example, the gravitational force we said is or the gravitational field is any region in space around the Earth where the gravitational force is felt. And the gravitational force is the force that tries to pull every object towards where? The center of the Earth. It's the force that tries to do what? Pull every object towards the what? So there is a law of gravity that says that what? Anything that goes up must come down. Why? Because there is a force that is acting on it. Outside the space beyond the gravitational influence of the Earth, anybody that goes up continues going. It doesn't come down. So that was why the last time I was in space, wanted to eat, was it bread and tea? Yes. So we now poured tea in the space. Then we took bread, okay, you remember, right? You see, I'm not lying because the story is consistent. All right, are we there? So I said that, so now, the gravitational force pulls every object towards the center of the Earth. So on Earth, where does all objects go? Down, right? So down is the center of gravity of the Earth. Is that okay? Do we understand that? All right. So now, in the 16th century, I think roughly about 1687, our classical physics man, Sir Isaac, he deserves this Sir, right? Sir Isaac Newton. That time we were made to Sir Isaac Newton, right? He proposed a law that is known as the law of gravitation. And it was one that even brought about the law of gravitation. Gravitation means pull, is that okay? Or some kind of attraction, is that okay? That's more of the root word from which gravity. Have you heard, I always gravitate towards something? Do you know what that means? It means I'm always drawn towards something, is that okay? So that's what gravity means, kind of. So he was the one that propounded a law known as the law of gravitation. Is that okay? So we call it the Newton's law of gravitation. So you're right now. Newton's law of gravitation states that the force of attraction between two bodies, the force F of attraction, between two masses, M1 and M2, between two masses, M1 and M2, is directly proportional to the product of the masses to the product of the masses and inversely proportional to the square of the distance between them. Use R for distance. Directly proportional to the product of the masses, but inversely proportional to the what? To the square of the distance between them. But at the end of the series of this gravitational field, we are going to be talking about the Kepler's law. So we said that the force now, so mathematically speaking now, can we face the board now? Mathematically speaking, the force of attraction is said should be directly proportional to the product of the masses m1 and m2, and that same force should be inversely proportional to the square of the distance between them. Now we are seeing another inverse square law. But how many inverse square law have we considered? We saw that of intensity of sound. Do you remember? That the intensity of sound is equal to E sub naught over D squared, right? Okay. We also saw in electric field, Coulomb's law, yeah? Do you remember? KQQ over R squared. So these are three inverse square laws that we have seen so far, okay? Now, so it's also called the inverse squared law, that's the point. It's also called the inverse squared law. So we know that this is the case. Now, what separates gravitational force from electric force is this. Gravitational force is always force of attraction, while electric force can be force of attraction or repulsion, depending on the charges. Is that okay? When we get there, you'll see now. So, if we introduce our constant of proportionality, we have F will be equal to, our constant of proportionality here is denoted by capital G. Is that okay? We call it gravitational constant. So, capital G will be introduced, and then we have M1, M2 over R squared. So, this is the force of gravity, the magnitude of the force of gravity. So, let's take a typical question. Oh no, let's just go on. We are going to take a question. We'll know how to use the formulas. Is that okay? Now, the next thing we should also learn of is now when a body is on Earth, I mean, as you on Earth now, the force of gravity acts on you and pulls your body down, isn't it? You know, as a body, you have mass. As an entity or as matter, you have mass, right? But gravity culminates in you what is called what? What does gravity culminate in you? Weight. Is that okay? Because of gravity, that is the reason why you have weight. So we say acceleration due to gravity. Acceleration due to gravity, or gravitational acceleration. So we say that weight of a body on Earth is equal to mg. Does that make sense? Now the value of g on Earth is what? About 9.8 meters per second square. Now it's stronger at the poles than at the equator, right? Okay, so that's why we approximate it to about 10 meters per second squared when we want to use the mathematics. Okay, but the point now is this, that without this gravitational acceleration, the entity will have only mass. Is that okay? Now, what's now the relationship between this weight that's acting on the body of mass m and this guy, this same force that's acting on it? Okay, so we know that weight is also a force, right? Right? Yes, sir. So we have that F weight will be equal to F. We are going to equate weight with our F so that we have mg will be equal to, now in this case, why we are equating is because we want to look at the force of gravity on you, the force of attraction between you and the Earth. Is that okay? The force of attraction between you, the body, and the Earth. So let's m be your mass, and let's m sub e be the mass of the Earth. Or m sub e, that makes sense, right? So the force on you is going to be equal to the force of attraction between you and the earth. Does that make sense? So we have M, that is U still, times ME, I'm going to introduce G, right? G, are you with me at all? Okay, G M E over R squared. Does this make sense to us? So M takes care of M, and then we have G will be equal to what? G M E over R squared. So this is the relationship between them. Is that clear to us? This relationship between them. Okay. Okay.
So G will be constant of 9 points.
Yeah, this G, the value of G is equal to what?
9.8.
No. This G has a value of 6.7 times 10 to the power minus 11. Value of G is what? Times 10 to the power minus 11. Well, what will be the units? The unit will be what? F Newton, right? You know that G here will be equal to FR squared over M1, M2. Does that make sense? So the unit of this guy was Newton meters squared over kilogram squared. So we say that this will be 6.7 GU will be equal to 6.7 times 10 to the power minus 11 Newton meters squared per kilogram squared. Does that make sense? So that's the value of G. Now, so let's test the hypothesis that this guy is actually going to give us 9.8. Now, we already know our G. G is given as 6.7 times 10 to the power minus 11. The mass of the Earth is about what? What's the mass of the Earth? The radius of the Earth, 6,400. What's the mass of the Earth? It's about 6 times 10 to the power 24. 6 times 10 to the power what? 24. That's the mass of the kg. So let's plug these values into this equation. Let's see if it will give us G will be equal to 6.7 times 10 to the minus 11 times mass of the Earth, 6 times 10 to the power 24. Are you with me? All over what? 6,400 squared. So G will be equal to 6 times this will be what? 24 minus 11 all over 64 squared. 64 squared is what? Or just square everything. 40, 96, 0, 0, 0, 0. So we have 40.2 times 10 to the power, this minus this, 13. All over here, you can just say this will become 40 and 4.096 times 10 to the power 1, 2, 3, 4, 5, 6, 7. 10 to the power 7. So this will become, divide 40.2 by 4.06. 40.2 divided by 4.02. 4.096 rather. 9.814 times 10 to the power here 13 minus 7. So is there times 10 to the power anything there? Okay. So this will be 9.8 times 10 to the power power 6. Now this 6 is supposed to leave now. What is supposed to give us 9.8, isn't it? And so there is an error somewhere. 64 times 64 again. The mass of the Earth is exactly that. Is this now? Okay, it's the radius of the Earth that is wrong. What's the radius of the Earth? Is it 6,400 or 64? Is it 6,400? 6,400 kilometers. So in meters, it will be 6,400,000 in meters. Is this clear? 000 all squared. So this will now become 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this will now be this times 10 raised to the power 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Exactly 13. So 13 minus 13. So we have 0 there. So the answer is this meters per second squared. Is that okay? So, alright, so let's put that down. Now let's talk about so we've talked about the relationship between weight and the gravitational, acceleration to gravity and the G. Is that okay? And let's talk about what is called the gravitational potential. Gravitational potential. So we have gravitational potential and gravitational potential energy. Gravitational potential and gravitational potential energy. Now, gravitational potential is the work done. Gravitational potential gravitational potential is the work done in bringing a unit mass of a body from infinity to any point on the Earth's surface. In bringing what? To a point on the Earth's surface. The unit mass of a body from infinity to any point on the Earth's surface. Is that okay? All right. So, gravitational potential, therefore, is given by, we said, gravitational potential, let's call it GP now for now, is what? The work done per unit mass of a body brought from infinity to that point. Is that okay? So work done here is going to be, listen, work done is going to be the gravitational potential energy. It's going to be what? Potential energy. Okay. So what that will mean from our formula is this. So work done first is going to gravitational potential energy. And what's the formula for work done? Force times distance, right? So if work done is force times distance, then we have our force is G m1 Now, since we are relating it to the mass of the Earth, so it's going to be m and me. Is that okay? So over r squared times r. Does this make sense? So this takes care of one. So the work done, or gravitational potential energy, GPE, is given as G m me over r. Is that okay? So but the gravitational potential is now the work done per unit mass brought from infinity to a point, right? Now actually, we always put a negative here in the formula for gravitational potential. We always put a negative because if we are coming from infinity, are you listening? Infinity is very great, isn't it? So if you are coming from infinity, what you are doing is you are doing work, you are doing negative work. Does that make sense to you? Do you understand? You know, if you count 1, 2, 3, positive. So we are coming from infinity. What are you doing? You are reducing the number, right? So that we say we are doing negative work. So because of that, we always put a negative. Do we understand now? So we have minus the work done, which is this. Does that make sense? So minus GP over R per, let me not confuse us. We said it's work done per unit mass, right? Are you with me? Okay, so this will now become, work done is now G M E over R, then over M. Does this make sense? So therefore, GP becomes G M E over R times M. Is that okay? So M takes care of M, so that gravitational potential of a body is going to be what? G M E, negative, don't forget the negative. Negative G M E over R. Is this clear? Is this clear? Okay. All right. So now the last equation that we generate is that of escape velocity. Is that okay? So what work must the body do to escape the gravitational pull of the Earth? But before that, now if a body, let's consider some 3 cases. If a body was on the surface of the Earth, watch now, a body of mass m is on the surface of the Earth, what will be the gravitational pull towards the center, separated by distance r? The gravitational pull, the force to experience is going to be what? G m, the mass, this one is m, the Earth has m sub e. Is that okay? So the gravitational pull will be G m e over radius of the Earth. Is that clear? But what if the second case, this first case, the second case, what if this body was outside the Earth, but within the region where the gravitational pull of the Earth can still influence it? In such a case, what will happen? So it is separated from the Earth, and notice the pull, the force of gravity, the distance we always consider is always the distance between the center of gravities of the guys, not the distance from here, to here. It's the distance from the center of gravity. For a regular object, the center of gravity is always at the center of the body, isn't it? Okay, so for example, I draw a regular object like a box like this now. So the center of gravity is somewhere around here, isn't it? Okay, so that's where the distance is being calculated from. Is that okay? The distance r is from the center of gravity of one to the other. And what's the center of gravity? The point on the body where the maximum weight is felt, right? Do you remember? Okay, so now the distance between this guy and the center of gravity here is going to be here, from here to here is already the radius of the Earth, right? And from here to here is going to be a particular distance h. Are you with me? So the pull on that body, gravitational force is going to be G is still body M, right? Then ME over what? R plus H all squared. Does that make sense? Does it make sense to us? Because here there's a distance between the earth and that guy and the body. Then for another body that is inside the earth now, this one is inside the earth, and the radius of the earth is still R. Is that okay? So there's some distance into the earth. So this one is going to be, the force that will be felt by this one is going to be F equal to, now watch. The distance between them now is not going to be R, nor just H, but it's going to be R minus H. Is that okay? Because it's already closer to the earth than the radius of the earth. Does that make sense? The distance is not as far as the radius of the earth again. So we have G M E over R minus H all squared. That's going to be the distance between them. Are we clear on that? So, but how can a body escape the gravitational pull of the earth? The body must possess a speed that is equal to what we call the escape velocity. And what is escape velocity? Let's see what escape velocity is. Now, the escape velocity, we said, is the minimum velocity to do what? That the body must possess in order to do what? In order to escape the gravitational pull of the earth, right? So, and what we basically do is that we transform, the body is going to have an energy that is called the gravitational potential energy, right? So we translate that to kinetic energy that the body must possess if it must move out of the earth, isn't it? So we're going to say that the GPE is going to be equal to what? Kinetic energy of the body. Is that okay? Okay, so now, and GP is what? GMME over R, right? That's GPE, not GP. Don't forget to, this is GP, GME over R. If you are confused, raise your hand. It confuses people, especially in this thing too, in electricity. You will not know the difference between electric field potential and electric field potential energy. Don't misplace them for each other. This guy is GP, gravitational potential. Work done in bringing a unit force from infinity to a point. But the work done by the body itself is going to be what? G M whatever over R squared. Do you understand now? So this is the gravitational potential energy. It's going to be equal to the kinetic energy of the body. So that will be half mv squared. Does that make sense? So from here we can cancel m out. Okay. If we cancel m out, what do we have? Then we have G me over R is equal to v squared over 2. So by the time we make the v subject, we have v squared is going to be, let's multiply this guy, vr is going to be equal to 2gme. Does that make sense? Divide both sides by r, so that v squared is equal to 2gme over r. Then we take square root of both sides, so that v equal to what? The square root of 2gme over r. So this is the escape, this is the formula for the escape velocity of a body that wants to escape the earth. Is that okay? The earth gravitational field. Are we good? So we said escape velocity is the minimum velocity that the body needs to escape the gravitational field of the earth. This is equal to root 2gr. Okay. There's also a relationship though between the mind you, this R is going to be The radius of the Earth, right? Isn't it? Time. Small g. Small g is what? GME over R squared. So where R is the radius of the Earth, so that was R squared, right? Okay, so look at something here. We can bring in this guy, since recall that G is equal to GME over R squared. Then we can say that this is GME over R squared. Okay, but there's no squared here, right? Okay. So it means that let's remove this. Let's remove one R here. It becomes RG is equal to GME over R. Do you believe with me? Is this clear to us?
Yes, sir.
See what I did? You know this is R times R. I brought one here. It becomes RG is equal to GME over R, right? So and this is GME over R, right? So our formula escape velocity can also be written as the square root of 2GR. Okay, this was the formula you were asking for then. Okay, so that's it. So we have two formulas. V equal to 2GME over R and this. Is that okay? Let's solve some questions.
How can we know G in the question different from this one?
No, G is acceleration to gravity 9.8 now. This big G is that value we gave you. We give you every time you have a question. You understand? Let's solve some question. Pause it, please. Now listen. Let me go from number 4 to number 1. Is that okay? So number 4 says, if the radius R of the Earth is 6.4 times 10 to the power 6 meters, and the acceleration due to gravity, G, is this. Calculate the escape velocity of the rocket. There are two formulas I gave you for escape velocity. V is equal to what? 2G over R. Okay, what's the second one? Root 2R, right? Now, what does this, can you say something about this formula? Now, one thing that is very clear from this formula is that the escape velocity does not depend on the body. So what does that mean? So anybody in the universe that wants to escape the gravitational field of the Earth must possess at least the answer you get here. Do you understand that? So whether it be a small biro or a whole house moving itself and wants to escape the gravitational field of the Earth, the escape velocity is always what? The same. The minimum velocity is always what? The same. In fact, that is the exact velocity that the body needs. Do you understand now? So because what you see here is the Earth universal gravitational constant, the mass of the Earth, not the mass of the body. Does that make sense? The radius of the Earth, not the distance separating them. I mean, of course, that's the distance over which is going to move, but it's a constant. All of what you see here are constants. So if I say which of these does not depend on the mass of the body, on the mass of the body here, A, gravitational force, B, gravitational potential, C, gravitational potential energy, E, escape velocity. Escape velocity is the one that does not depend on the mass. Whatever the mass of the body is, the escape velocity is the same. Is that okay? All right. So here, from our parameters, let's write our parameters out, then we'll know what to use. R is giving us 6.4 times 10 to the power 6. Don't make the mistake we made the other time. That one we wrote was in kilometers from longitude and latitude. And acceleration due to gravity, G, everybody knows is 9.8 meters per second square. Calculate escape velocity. So considering these two values we have by using this formula. So V will be equal to what? The square root of 2 times 6.4 times 9.8 times 10 raised to the power 6. By the time you solve that, you're going to get 1.11 times 10 raised to the power 3. Is that okay? So which will be 11 kilometers per seconds. Does that make sense? All right. Is it clear to us? Okay. Now, give me, okay, now let's solve number 3, yes?
The answer is 11.2.
11.2, yeah. 11.2 times about 3, yes. Okay. So should I solve number 3 now? Where is it just now? So I'll clean here. Okay, so the values of x, y, and z respectively in the expression m superscript x, y, l to y and t raised to the power z. So it says you find the value of x, y, and z. Okay, so of course this one represents mass, m will represent what? Mass. This is just dimensional analysis. L represents what? Length. And T represents what? Time. Does that make sense? So it says for the universal gravitational constant G. So what we have to do first is to write the dimension. What we want to do is just write the dimension for G. Is that okay? Okay, so we say that basically, you can even say that m to the x, L to the y, T to the z will be equal to, first, what is G? You recall that F is equal to G M M E over R squared, yeah? Okay, if this is the case, then G will be equal to what? F R squared over M M E. Do you remember? Okay, now, it could be any M, it could be any M, so let's just say mm. Do you know why? Because it will be include its dimensions is units now that we are considering. All right, or quantities rather, quantities that we are considering. So whether it's m1, m2, as far as its mass is the same. Okay, so in this case we have what? F times R squared over mm. So mm is already seen as look-alike, right? Okay, so in this case we can bring them together and say m squared. Okay, so if that's the case, then we have m x l to the y t to the z will be equal to force is mass times acceleration, right? Times r looks like length. R is length, distance, right? So we have r squared, which is l squared over m squared, or m times m if you care. So you now have m to the x, l to the x, y, t to the z. If you don't understand what I'm doing, raise your hand. Okay, is equal to m times, what is this acceleration? Velocity over time. So that becomes velocity over time. And we can still break this one down, right? Velocity becomes length over time. Do you remember? Distance over time or displacement over time. So that will be L over T over T. That becomes what? L over T squared. Do you get that? So it means acceleration can be written as L over T squared times L squared. Okay? Then all over M times M. So in this case, we can merge this so that this guy will become ml cubed all over t squared times m times n. M takes care of one m, right? So in that case, we'll have that m to the x, l to the y, t to the z will be equal to what? Let's write everything as in one straight line. So we have L as denominators, L cubed numerators rather. T raised to power minus 2, M raised to power minus 1. Does this make sense? So M raised to power X will look like M raised to power minus 1, right? So M raised to power X will look like M raised to power minus 1. So if the bases are the same, the powers must be the same. Does this make sense? L to the Y will look like L cubed. The bases are the same, the powers must be the same. Then T
minus, okay, because it's the denominator.
is the normal numerator. So these ones that were brought from under are the ones that will have minus. Okay. So then T to the Z will look like T raised by minus 2. Then if the bases are the same too, the powers must be the same. So what do we have? X is minus 1, Y is 3, minus 2. So the answer is B. Are we clear on that? Then let's solve number 3. I was trying to bring out something here. What can we bring out? This. We have not brought anything out because it's the R, right? So R times R becomes GME over R squared, confirming G. Isn't it? Okay, now watch me. Number 3 says number 2, right? The force experienced by an object of mass this. So the mass of the object is 60 kg. In the moon's gravitational field is that. In the moon's gravitational field is that. So the magnitude of the force. Now this is force in the moon's gravitational field. So let's say F sub m, gravitational field of the moon, is 1.002 times 10 to the power 2. What is the intensity of the gravitational field? What is the intensity of the gravitational field? Now listen, under fields, anytime you hear of intensity, is always force. See, what does intensity mean? For example, it's best explained with electric fields. In electric field, if I have a point charge, the point charge is going to have its field all around it, right? Surrounding it. So it means that any body or any charge that makes its way into this field is going to feel a force due to this charge. Does that make sense? Yes. So for this case, it's going to be a force of attraction. Are you listening to me? So, but the magnitude of the force that it will feel is dependent on the distance of separation. For example, for this negative charge here and this other negative charge here, who do you think will feel more force? We have A and charge B. Charge B, right? Because it's closer to this guy, isn't it? But of course, we also know that so with this way we now define intensity. Intensity is the force felt per unit of anything placed in that field. Does that make sense now? So what this means for this case will be that the force, the electric force per 1 coulomb of charge placed in that point. The only vector field that we don't use this, that intensity is not equal to this, is the magnetic field. Why? Who can tell me why? Why is it that now in gravitational field, it will be the force, gravitational field intensity will be the force per unit of what? Of mass placed at a point. Is that okay? Okay. So now, why is it that in magnetic field we cannot have force per unit of whatever place? A monopole. Because of the absence of what? Monopole. So because electric field is magnetic field is always a dipole, we cannot have magnetic intensity to be the force, the magnetic force per unit of pole. No. Do you understand? So that's the only case that is exceptional. All right. So in this case, the gravitational field intensity, let's call it E sub G, will be equal to the force per unit of mass. Does that make sense now? Okay, so what's the force in this case? 1.002 times 10 raised to the power 2 over what's the mass? 60. So this becomes what? 6.01617 times 10 raised to the power. Is that all? You just divide this by this, right? No. Well, this divided by this should give you minus something. Divide 1.002 by 60. Zero point 0.0167 times 10 raised to the power 2. So this becomes 1, 2. Cancels this, right? So 1.67. Now this will be 1.67 Newton per what? Per kilograms. Is that okay? Let's see it. More questions. Questions are not much under this topic. Where did I get the question from? What happened? Now let's go to the next field, which is the electric field. Now, what is the electric field? The electric field is any region in space where the electric force can be felt. Do we understand? Or is felt? In order to understand electric field, see, there are so many things to talk about. So because I'll just link a video in the description to talk about the many things for us. I'll just touch on some things, and basically I'm going to talk about the calculation aspects more. But before we talk about those, get to the calculation aspects. Now, we know that charges exist. Is that okay? Charges exist. So we have two types of charges according to Benjamin Franklin. He said we have the positive charge and the negative charge. Is that okay? And according to the same guy, we said that, is it according to Benjamin Franklin? Or generally we just agree that for positive charges, there is always an electric field around each charge. Is that okay? Each charge always has an electric field. The positive charge, when you say a body is positively charged overall, what it means is that the body, since every atom consists of proton and neutron, positive charge and negative charge essentially. So when I say a body is overall positively charged, it means that that body has lost what? An electron. If I say a body is negatively charged, it means the body has what? Gained an electron. You don't lose proton, except in a nuclear reaction. Is that okay? Except in a nuclear reaction. So if and the law of electrostatics is that what? The fundamental law of electrostatics is that what? Like charges repel and unlike charges attract. So for example, these charges we have here, they are going to attract each other, and if there are similar charges, they are going to repel. But before we do that, let's talk about the electric field that is around each charge. So for a point positive charge, you can have a monopole for a charge. Do you understand? Because a charge can exist on its own. So for a charge like this now, you know, yesterday we were talking about how light is made. So this guy now, okay, but let's not get to it again. Now this guy now is going to have electric field that is represented by electric field lines that proceeds radially outward from a point positive. Is that okay? So from a point positive charge, the arrows will face where? Outward. For a point negative charge, the arrow will face inward. So that if I say that the point of attraction, the whatever of attraction is towards where? Or where is the attractive force moving? In what direction? You will know it's always in direction of what? Negative charge. Do we understand?
Yes.
Because for negative charge is always the electric field lines are drawn so that it's showing inward. So when the law of electricity says that like charges repel and unlike charges attract, this is what it means. That these guys, which are unlike charges, are going to attract themselves this way. The electric field lines will go out from here and into negative. So out from here into negative, out from here into negative, out from here into negative. They usually have a curvilinear path. Is that okay? They usually have what? A curvilinear path. That's how we say it's radial. Do we get it? And some characteristics of electric field lines, they are what? They never meet or cross each other. Instead of cross each other, what would they create? They will create what? A neutral point. They will create what? A neutral point where the electric force will not be felt at all. Is that okay? So for example, if I have a point positive charge and another point positive charge, the electric field lines will go like this. The electric field lines of this one will go like this. Now what will happen is this. It's going outward here, going outward here. Outward, 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 outward. Outward, 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 outward. Now here's what will happen. The moment they want to meet each other, there will be a deflection. Is that okay? This one will deflect away radially. Is that okay? So this one too will deflect. There was one coming like this. It will deflect away radially. This one will deflect away radially. So there will be a point here that is created that is called what? The neutral point. Are we clear? So at this point, there's no force felt at all. Is that okay? Or no electric force acting at that point. So the forces repel each other. Are we clear? Okay. Now we have electric field lines. We've done that. So we've said they never meet or cross each other. They always go out radially outward from positive, radially inward for negative. Then another thing is that they are strongest. The closer the electric field lines, or the more concentrated the electric field lines are, the stronger the electric force. So what that is saying is this: if I have a point negative positive charge here like this now, then someone might ask, Master, why do you like positive charge? Because I'm a positive person. Now, so where are these charges closest to each other? For example, look at this path here and this path here. This orbit A and this orbit B. Which orbit is closer to the charge? Which orbit will have the strongest electric force be felt? Orbit B, because the closer the electric field lines are, the stronger the force, just like magnetic field. Is that okay? All right. Now, there are two types of materials based on their conductivity. We have the conductors and the non-conductors. The conductors are the ones that allow electricity to pass through them, and the non-conductors do not allow electricity to pass through them. Now, but all bodies have electric property. Is that okay? All bodies in the universe have electric property. Only that I told you about the fact that there is a conduction layer, a conduction zone around atoms, right? So the reason why non-conductors, another name for non-conductors is what? Insulators, right? The insulators used in capacitors are also called what? Dielectrics. They are called what? Dielectrics. So the reason why insulators are insulators is because the charge, the charge, the charge, the charge concentration, the electrons are not free. Is that okay? The electrons are not what? Free. And the reason why they are not free also is because of the fact that the conduction band and the last energy level are very far apart. I told you that before, right? So this conduction band, so that electron, for it to be mobile, for it to be free, it needs a particular amount of energy to escape that conduction band for that body to become conductive. Is that okay?
Yes, sir.
But the conductors, the conduction band and the last energy level and the electron shells, they are very close, more like they even overlap each other. Is that okay?
Yes,
so that's why a little surge like this, they conduct electricity. Is that okay? All right, now one of the things they noticed in the olden days is that if you rub piece of stuffs together, if you rub stuff together, they will gain charges, they will become charged. So for example, if you rub plastic on your hair, it will become what? Charged, right? Now what charge will it become? Your hair will always become what? Positively charged. Then the guy will now become negative charge. If I rub silk and if I rub glass on four of animal, what will it give me? Which one will become positive, which one will become negative? Positive, rod, negative. Do you get it? All right. So, is that clear to us? Okay. So now let's get to the concept of charging. I'm just trying to go over some stuffs. Now, for the concept of charging now, the way we charge, there are two ways. There are three methods of charging. We have charging by contact or by friction, and charging by induction, and charging by
Induction.
we call it induction charging. So the way by which we charge non-conductors, we charge non-conductors by friction. Then we charge conductors by contact and by induction. Is that okay? Now let's go over friction charging. So for charging by friction, what we basically do is what we are doing there. You will rub that thing, those two guys on each other, and what will happen is that there will be a separation of charge. Another reason why we also say that this guy, non-conductors do not conduct, is also that the number of positive charges are equal to the number of negative charges. Do you understand? So basically it's for an uncharged body. For an uncharged body, number of positive charge equal to the number of negative charge. So for example, what will happen is this: if I rub this piece of clothing material, if it was a wool material, what will happen is this: by the time I rub it with a rod, the rod too is also positive, has equal distribution of positive and negative charges. What will happen is this: by the time you rub, some positive charges will by the time you rub, this is the 4, right? 4 always get the positive charge, right? So from positive charge, we will move here. So this guy will have higher concentration of positive charges. The negative charges will now be more here, right? So we have higher concentration of negative charges. So what will now happen is that by the time you bring this guy close to a piece of material, such as a tiny paper. So that tiny paper to add equal distribution of positive and negative charges before. By the time you now bring this guy that has more negative charge and positive charge, you bring it close to it, this guy will now separate charges. So positives might go to this end, and negatives will come to this end. Then this guy is attracted to your piece of paper. You use it to pick it, like some of you are practicing already and are no longer listening to me. Okay, so how do we now charge by contact? Here is charging by contact. We charge by contact this way. We only charge conductors by contact and conductors by induction. Now this is conductor charging, by contact charging. That's the way by which we normally charge the electrophorus. What's an electrophorus? It's a device that is used to what? Detect charge. Is that okay? The electroscope. It's electrophorus. Electrophorus is used to store charge. Electroscope, like a capacitor, yes. Electroscope is used to what? Detect charge. The typical is also used to store charge, as in when it's charged. But of course, you don't get charges from it, unlike capacitor. So, for example, we have the gold leaf electroscope. If you want to see, understand it better, I'm going to link a video in the description. You'll see everything about electric field. So I'm just going over a little bit of things. So we have charging by, the most common question you will see is charging by induction. Induction charging is, there is no contact. So we bring a charged body. For contact charging, there must be touching. When induction charging, there is no contact. So a piece of charged rod is brought close to a body that is the conductor that is to be charged. So what will happen is this, there's also equal distribution of positive and negative on this body, right? Because it's uncharged. The moment you bring this guy close to it, the positive charges will now separate. This guy is negatively charged, right? So this end of the guy will now do what? Become what? Positively charged, because law of electrostatic, unlike charges attract. So those positive charges will now aggregate themselves here. Negative charges will now aggregate themselves at this end. Does that make sense? Okay, so that's the way charge distribution occurs, and this body is said to be charged. Now, the moment this body too is taken away from here, it might lose its charge. Is that okay? All right. Now, so we've done that. Then we also talked about something about the fact that on this sphere, for example, where is charge concentration going to be higher? A point A, B point B, C point C, D point D. Where is charge concentration going to be higher? Point D. Point B, the right? The answer is point D. So, and that is because the more the edges, charges are usually more concentrated on edges. If you have noticed, if you have a metal table at home before, what you use right now, the metal table at home, that has happened to me before I leave this woman. There he is a welder, so he made metal stores, metal screw, metal. So there was a metal table at home. So the edge of that table, one such day I was just, I don't know, it was my leg that touched it, this edge, and I got shock. One tiny tingly feeling though, but it was still a shock, and it was during the dry season. Yes, on my leg.
Yes.
Has it ever happened to you?
Yes, if you are not striking net.
Another one is, do you know now the doorknob?
Yes.
If you have touched the doorknob before, or the edge of the doorknob, so you get it. So that is, charge always concentrates at themselves at edges of materials. Is that okay? So, okay, now there is a question that they usually ask about charging metal spheres. So I have a piece of a metal sphere. Are you with me? That is charged, and I have another metal sphere that is uncharged. Are you with me now? This guy is charged with negative charges. For example, this guy is uncharged, so it has equal distribution of positive and negative, isn't it? That was what we said. So what will happen is this: if you want to charge this sphere, the way the question usually comes out is this: if you want to charge this sphere, this is the way it is. Let me explain the condition for you. To charge this sphere, do you remember the video you guys saw? So what happened? The man brought this sphere close to this guy. Is that okay? It's close. It doesn't have to touch it. The moment it is close to it, in fact, you might see sparks anyway, because charges are jumping. Is that okay? So negative, positive charges, which one will aggregate themselves here? Negative or positive? Positive charges will aggregate themselves here, and negative charges will aggregate themselves here. Is that okay? If this guy was removed, or if this guy were removed, immediately after doing this, after bringing it close, if it were removed, what will happen to this sphere? To discharge. Is that okay? How do you keep it charged? You earth it. So you see this negative charge, you conduct it to the earth. Is that okay? It's called earthing. Okay, we're going to do electrical components and diagrams so that you know them. So we earth it. By earthing, what happens? These negative charges do what? Flow to the earth. Is that okay? And earth is the only thing that can never be overcharged. Is that okay? That's why when you conduct all charges to the earth, nothing will happen. Is that okay? Except if it were a wet surface now, because some of my thinking that what if there's a naked wire on the floor and then it's wet and then people get shocked? Yes, because there's a conduction there. But the earth itself will not conduct the electricity because it has maximum amount of plus and negative charges, so it cannot be overcharged. So we earth this guy. What we come out with is what? A sphere B that looks like this: positive, 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 positive. So after earthing, you can now remove this guy as while this guy is still being earthed. Is that okay? You can remove this guy. So this guy will remain charged. Are we clear? Okay. Now, the next thing we have to see is, I think we can go on to calculations now. Are we good now? Let's go on to calculations now. So now, we already ascertained that between two charges, there is equal amount of between two charges, there is a force of attraction or repulsion here. Okay, so if there is a force of attraction or repulsion, this is what happens. The Coulomb's law comes to stay, right? Or comes to play, isn't it? It was named after who? Charles Augustus Coulomb. And Coulomb's law states that what? The force of attraction between 2 point charges is directly proportional to the product of the charges Q1, Q2, but inversely proportional to the square of the distance between them, right? You can write it the way we wrote the other one. F is inversely proportional to the square of distance. So the second inverse square law. Do you remember now? Please follow me well now in this part. Okay. So we now have that F will be equal to, introduce a constant proportionality, K, Q1, Q2 over R squared. Now, K here is given by the formula 1 over 4 pi epsilon naught. What is epsilon here? It's got permittivity of free space. That gave us the song relative permittivity. Okay, we've not gotten there. Now there is also relative permittivity. Simply means how much a space is allowing for conduction of electricity. Is that okay? So permittivity. So an epsilon naught is given by the value 8.85 times 10 to the power minus 12. Is that okay? So first, let's get a value for K, a unit for K. So K here will become what? F times this, FR squared over Q1, Q2. This becomes K equal to what? Newton meter squared per Coulomb squared. This is just a different version of that former one. That was Newton meter squared per kilogram squared. Okay. So now let's calculate the value for K. So K will become what? 1 over 4 times pi, 20 over 7, that's 3.142 times epsilon naught, 8.85 times 10 to the power minus 2. This was experimentally determined by Coulomb. So what is the value of K then? 9 times 10 to the power 9 Newton meter squared per Coulomb squared. Is that okay? Albeit you don't need to cram this constant to be given in your exam, but you just need to know how it was gotten or generated. Are we good? Now, we know that for a point positive charge or for a point negative charge, for a positive charge, we are going to experience a positive charge. We have an electric field about it like this that is going to go radially outward, right? So the strength of the field or the strength of the force felt due to this field is given as this. We call it electric field intensity. We call it what?
Electric field intensity.
Or electric field strength. Or what?
Electric field.
That is how strong the electric field is. And it is a vector quantity. So electric field strength is given by the force per unit of charge placed at that point. What is electric field strength? The force per unit of charge placed at any point on the electric field of that guy. So this Q, okay, good. This charge here that we are measuring is electric field intensity will be called, we are obstructing that girl, will be called the source charge. This will be called the what?
Source charge.
So this is the source charge. And the charge that we are bringing to the point, or to whatever point, is going to be the what? The test charge. So this Q here is going to be the value of the what? Of the test charge. The force per unit of the test charge. Are we there? But we already know that there's going to be a force of attraction or repulsion between the test charge and the source charge, right?
Yes, sir.
The strength that I want to feel there is either strength of a pull or strength of a push. I've told you that that's what separates gravitational force from electric force. Another thing is that gravitational force is very, very weak. You understand? That is why objects are not pulling into the earth, such as the moon. Is that okay? Because the gravitational force is very weak compared to the electric force. You saw the value of the constant, right? So the value of the constant is in trillions degree greater than the, what's that trillion? It's great. I think it's even greater than trillions. Look at this. And compared to the G value, what did we get for G value? 6.767 times 10 to the power minus 11. You see how far apart they are. So that's why the electric force is greater than the gravitational force. Okay, so I said that the field, the strength that it wants to feel is just a force of either of attraction or what? Repulsion. So let's say if it was a test charge that was negative, what force will it feel? Attractive, right? So we want to know the magnitude of the attractive force. Keeping in mind that F, let's call the test charge big Q. Let's call the source charge big Q, the test charge small q. We already know that force is already K Q1 Q2 over R squared, right? And I told you already that the distance between them also matters. So that as the farther away you are from the field, what will happen to your force? Is it the higher the force you feel? No, the lower the force that you feel. So we have that F therefore becomes, so, and we know that E now is the force per unit of charge, and F is this. So we have KQQ over R squared per unit of charge, right? Whenever you are dividing by a whole number, you have F over Q will be equal to what? E rather, will be equal to what? KQQ over what? R squared times Q. Q takes care of Q. Now watch. So E will now become what? KQ over R squared. This is the second formula, so this equation, let's call this equation 1. Let's call this equation 2. Let's call this equation 3. Now, this is another equation for electric field intensity, but this Q here will be what? The source charge. Is that clear?
Yes.
So this electric field intensity due to the source charge, the charge producing the field itself. So this is the formula you use. Okay. And you will not be told source charge. I'm just telling you the difference so that you know what those formulas mean. Okay. Let's go to the next thing, which is electric field potential and electric field potential energy. You see now, you see they are all related. Those field forces, they are all related. Well, they always have an intensity, which is dependent on the distance that you have from them. Is that okay? So now, the next thing is electric field potential. Just like we did the other time. In order to understand electric field potential, we must know electric field potential energy. Is that okay? Electric field potential is represented by V. Let me first explain something to you. If I have a source charge here, are you with me? And I have a particular charge at a point X. I want to bring it. You know that this guy, the field is going like this, right? So I don't need to draw it. Now, if I want to bring this charge from point X to point Y, now, if I want to bring this force, this charge to point Y, am I doing work against or I'm doing work for? Like naturally, I'm doing work what? Against the field. Does that make sense now? Because it will be harder to bring, okay, between this point Y and point Z, which one is easier to bring the positive charge to? Point Z. In fact, naturally, the plus charge will go towards what? Point Z. And that reduces the potential energy. Is that okay? But if you do work against the field, you will increase the potential energy of the charge. Does that make sense? Does that make sense? So it means that the potential energy, the electric potential energy is going to be the work done by the charge in moving from one point to the other. Is that okay? So, and work done is given as what? Force. So that will be work done. It's given by what? Force times distance again. Do you remember again? So the work done by the charge is going to be force, which is Q1, let's just be Q and small q henceforth now, over R squared times R. R takes care of 1R, and then W will be equal to what? KQQ over R. This makes sense here? Okay. Now, if this is the case, now what is now, so we know when this energy will increase now, right? Same for a negative charge. If I had a negative charge, if I bring a point positive from a point X here to a point Y here, what will happen to the potential energy? Now I want you to answer. Will the potential energy increase or decrease? It will what? Increase. Okay. Deborah, will the potential energy increase or decrease? Increase. What will happen to the potential energy to it will know? It will decrease. Potential energy will decrease. Okay, can you explain why? Because naturally there will be attraction. So the work that it has to do decreases. It's when you want to abstract it away, there's already a force that is pulling it towards here. You want to now take it away from that point to a point Z, for example, then the potential energy will now do what? Increase. If you don't still understand, raise your hand. Who else does not understand? Does the boy understand? This guy is at a point X. We want to bring it to a point Y and a point Z. There are 2 points that we can possibly bring it to. Now, this guy, these two forces, Deborah, what kind of force is between them, attractive or repulsive? repulsive because they are similar charges. That makes sense. Okay, so I now want to do something. I want to bring this guy that is already being repelled, I want to bring it to a point that is close enough to this plus charge. Keep in mind that the closer you are to the force, to the charge, the higher the force of repulsion that you will feel. Does that make sense? So you're now bringing this guy towards here. What does that mean? That means that you are doing work against the field. You are doing work against the field. The potential energy of this guy will keep what? Increasing. The potential energy is like the potential to go away, right? You understand, to be pushed apart. So that potential energy will keep increasing. But if I wanted to bring it to this point, I don't even need to do any work. The potential energy will decrease. Why? Because their natural potential is to do what? To move away, because the force is repulsive already. But here, the force here is positive. I want to bring it to this point where there is negative charge. I don't need to do much work. Why? Because it's already what? Attractive. The force is already attractive. So it will naturally bring the positive charge towards itself. So the potential energy of this guy will reduce. But I wanted to take it, abstract it from a field that is drawing it close. Then I have to do more work on this body. Do you understand now? Because I will now be working against the field. Does that make sense? Okay. Okay, so that said, that will make us understand electric potential well. So now, we have said that electric potential energy is the work done, right, by a charge in moving from one point to another. So what is now electric field potential? Electric field potential is the work done in bringing a point, we usually use positive charge, or just a point charge from infinity to a point around an electric field. Is that okay? The work done in bringing, so we say it's the work done per unit of charge. The work done per unit of, is this charge going to be the test charge or the source charge? Test charge. Is it clear? Okay. So V therefore can become, what is work done? What is work done? Work done is already force times R, right? So over Q. Recall from here that F can be equal to what? EQ. Does this make sense? Just use FEC to remember. So if that guy is EQ, then we can have that V can be equal to EQ dot R over Q. So it means that V equal to what? ER. Okay. Now this is electric field of the source charge. Now, is it clear? Electric field of the source charge of the test charge. And I'm just trying to make you understand. When you see your question, you know what formula to use. Is that okay? Alright, so V can also be, since is work done per unit charge, work done is F times R over Q. Then we know that F is what? KQQ dot R over R squared dot Q. Does this make sense? I just brought this directly. Is that okay? Okay, so this takes care of this. This takes care of this. Then we have what? V will be equal to what? KQ over R. Does this make sense? This Q will be what? Which? Source charge. So you are getting it now, right? Good. All right. All right. So another thing you should now understand is that so the natural tendency of things is that a higher electric field wants to become lower in intensity in its electricity tends charges will tend to move from a point of high potential to a point of low potential, and that's what constitutes in electricity. That's what constitutes in what? Okay. So should we do this already, or we should go to electric current electricity? Let's do questions on this. Pause. Now, what is a capacitor? Before we start solving questions, let's just wrap up with capacitors. Now, what is a capacitor? A capacitor is a device that is used to store electric charges. Is that okay? Now we have the common capacitors are the parallel plate capacitors. Is that okay? And we call them parallel plate because they primarily use parallel plates. Is that okay? They consist of parallel plates. So this is one plate, and there's another plate that'll be here. So between them, these two guys are separated by a distance. Does that make sense? Okay. Now, then we'll connect them this way. Is that okay? So electricity will now run. Is that clear? Okay. But the basic idea is this now. The capacity of a capacitor to store electric charge is called what? Capacitance. So we say the capacitance of a capacitor is the capacity of the capacitor to store electric charges. Capacitance is measured in farad. Capacitor is measured in what?
Farad.
And there are many units of farad. The ones you will see in your JAMB is basically millifarad, which means what? Times 10 to the power minus 3. Millifarad. Mil farad, which means what?
Times 10 to the power minus 6.
Good. You also see nanofarad, which means what?
Times 10 to the power minus 9.
Well, if possible, the highest. 9, thank you. The highest you will see is that 12 that I wrote there, which is what? Picofarad. Times 10 to the power what?
Minus 12.
Is that okay? And there's also 15. I think that one is zeta also. But you will not see. There's no 100. So it's stored in farad. Is that okay? And farad is a very huge number. That's why we have millifarad, microfarad, and like that. Are you with me?
Yes,
sir. So we say that the capacitance. Are you listening to me now? Now the capacitance of a capacitor is given by the formula, or in fact the definition is also that the quantity of charge stored per voltage of electricity running, per voltage of electricity connected across its end. The quantity of charge per what? Voltage. Know ye also that positive one of it will gain positive charge, the other end will gain negative charge. So in this case, since we have that, capacitance is going to be what? Charge per voltage. That means that charge is going to be what? CV. Does this make sense? Right now, there are some conditions that affect the capacitance of a capacitor. The capacitance of a capacitor is directly proportional to the area of the plates. Is directly proportional to what? Area of the plates. So the larger the plates, the broader the plates, the what? The more the capacitance and the more charges it will store. Okay? The capacitance is also inversely proportional to the distance. Is that okay? Between the plates. The distance between the plates. Is that okay? So, if that's the case, we have that we are inversely proportional rather to the distance between the plates. So we now have, if we combine that, we directly proportional to A over D. Now we have a constant of proportionality here too, which is epsilon naught. So C will be equal to epsilon naught A over D. Is that okay? This formula relates them. So if I increase the area of my capacitor, A, it will store more charge. B, it will lose more charge. C, it will store less charge. C, I don't know anything about this thing in life. To store more charge. You didn't put in life now. Are you with me? So this is the case, right? Now there's something called relative permittivity, depending on the material you use. So we have relative what? Relative permitter. So we call it epsilon naught, epsilon r. Is that okay?
Yes.
Relative permittivity is given by the permittivity of free space, epsilon naught. Sorry. Is given by permittivity of material or medium over permittivity of free space. Is that okay? All right. Permittivity of free space is constant. We know that one, right? We did it here. 8 points.
85 times 10 to the power.
Okay. All these should be given. If you want to get permittivity of a material, it's going to be what? Of a medium, rather. Permittivity of a medium is what? Epsilon r. Some say epsilon. 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 Are we there? Alright, so this is the first set of equations that we have for capacitance. Now, energy stored in the capacitor. Energy stored in a capacitor. We just take the integral of this guy, and then we are going to have the energy stored. When we take the integral, we're going to have E equal to what? Half CV squared. Energy stored is going to be what? Okay, so you can have, since from here C is equal to Q over V, then we can say that E is going to be 1 over 2, C is Q over V, right? Dot V squared, right? So E is also equal to what? Half QV, or QV over 2. Does that make sense? Like many ways you can just invert the formula and all. Okay, now the arrangement you give to your capacitors, or the method of arrangement of your capacitor, also determines the capacitance, the quantity of charge that will be stored. Are you with me?
Yes,
okay. Yes. Let me clean this, please. So there are two ways we can arrange our capacitors. Is that we arrange our capacitor in series. What does series mean? When I say serially, it means they are following each other, right, consecutively. So first, when we get to current electricity, what we'll start with is what we use to denote different things. Is that okay? The symbols of different electrical components. Is that okay? The symbol for this guy is this, because it's a parallel plate. So you see it's parallel, right?
Yes, sir.
So this series arrangement, this connected to this, connected to this, connected to this, connected to this, and like that. This series. It's not just in capacitors. Once you see this arrangement following each other like this, is what? Series. Whether it's resistor, voltage. You get what I'm saying now? Series. Now, the equivalent capacitance here is given by 1 over C is equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus ... 1 over Cn. Any amount. Is that okay? Do you remember this?
Yes, sir.
Okay. Now, for those of you that normally forget things, remember that if I arrange voltage, look at this. What's this? What's this going to be called? A battery, right? Good. Now, how do we get the voltage of this battery? We add V1 plus V2 plus V3 plus V4. Provided that this was C1, C2, C3, C4, C5, all like that. You hear what I'm saying? Now, this guy here, the voltage are in series. So we add V1 plus V2 plus V3 plus V4. Watch. For those of you that normally get confused, I'm going to show you a trick now. You see this? What's the relationship between C and V? Is it direct or inverse? Inverse, right? So for C, so you remember, this one is sure for you, right? You remember this one? You cannot arrange voltage in series and now start saying 1 over V, right? Okay. So just say anyone that is inversely proportional to V, the series arrangement will be inverse. Does that make sense?
Yeah.
So for example now, look at this formula, V equal to IR. Resistance is directly proportional to voltage, right? But current is not, because in power we know that current is what? Inversely proportional to voltage. Are you with me? So watch this. Resistance is directly proportional to voltage. So if I arrange resistance in series, equivalent resistance 2 will equal to what? R1 plus R2, just like voltage. Because voltage and resistance are directly proportional. So all the guys that are directly proportional to voltage, their serial arrangement will go like this. Is that okay? Okay. Now, how about capacitors in series? Now, in parallel. How do you know capacitors are in parallel? Once they are separated by at least 2 junctions, right? So we have in parallel. In parallel, this is what we have. In parallel, we have something like this. Oh, sorry. Whether they are exactly under each other or not. These guys are in parallel. These guys are in what? C1, C2, C3. They are in parallel. Because a junction separate 2 junctions separate them. Is that okay? 2 junctions. Before, for example, if we are moving now here, we'll first get to this guy, go across it. Before we now get to this guy, go across it. We can't jump. Is that okay? It has to move through the wire. So they are separated by junctions. So this is parallel. This is what? Okay, so is this arrangement parallel? Let me ask you. Is this arrangement parallel?
No, sir.
This one?
No, sir. It is parallel.
So this arrangement is not parallel. Because if you move here, you won't get to a junction until you flow here. There's no junction between them. These are the 2 junctions there. Is that okay? Except if I put this here now. Yes, this is a junction here now. Do you understand now? This is a junction here. So once they are separated by junction, this will be what? Parallel. What if I now bring one here like this? Are these 3 in parallel, or which 2 are in series? Or all of them? Look at it well. Yes, all of them are in parallel because this is a junction here, this is another junction here. Are we clear? Is it clear? Don't get confused though. Look at, so that's it. When we solve question, you become better at it. Now, if you arrange in series, so equivalent capacitance or total capacitance will be equal to what? C1 plus C2 plus C3 plus Cn. Is that okay? In parallel. All right. So I guess we're good. Let's solve some questions now. Please. Okay, this is number 7. We just okay. So the first one says we have this system, and the diagram above shows 3. If you are unable to solve this, raise your hand. You are not able to solve it. The diagram above shows 3 capacitors C1, C2, and C3 of capacitances 2, 6, and 3. The potential difference across C1, C2, and C3 are what? So we are supposed to get the potential difference across them. In order to understand it, get the potential difference across them, first, let's get the charge flowing through. Is that okay? Or quantity of charge being delivered by the volts there. So how do we get that? Let's get the total capacitance or resultant capacitance there. So resultant capacitance is going to be, what arrangement is that?
Series.
Series, they are following each other. Is that okay? They are following each other, so that's series. So in series, you have that 1 over C will be equal to 1 over C1 plus 1 over C2 plus 1 over C3. So in this case, because there are three guys there, three capacitors. So we have 1 over 2 plus 1 over 3 plus 1 over 6. So the LCM of 2, 3, 6 is 6. 2 in this, 3 by 3 plus 2, right? Plus 6 in 6, 1 times 1, 1. So 1 over C equals, 1 over C will be equal to, this plus this, 6 over 6. That's 1, right? So C is equal to 1. Does that make sense? 1 mil farad. Okay? If C is 1 mil farad, so what's the total charge flowing throughout? Are we there? Or what's the charge being delivered to that guy? So we'll have, let's bring it here. We know that C is equal to 1 mil farad now. Q is what? If voltage is 12. So what's the charge flowing? Charge will be equal to what? C times V. That will be equal to 12 times 1. It's still 12 now. So 12 volts is being delivered to those guys. So now, in answer to calculate the what? The potential difference across each one. So potential difference across each one, V across each one, will be charge per capacitance. Does that make sense? Okay, the charge per capacitance. And what's the charge flowing through everybody? 12 over what's the capacitance of the first guy? 2. That becomes what? 6, right? Okay, 6 volts. Then for the next guy, that will be V1. Potential difference across the second guy will also what? The charge per capacitance 2. Does that make sense? So V2 will be equal to the charge 12 over 3. That becomes what? 4. Okay. 12 over 6. That what? 2 volts. Then the third one, V3, will be charge per capacitance 3. That becomes 12 over 3. That is what? 4 volts. Is that okay? What you will notice is that at the end of the day, the total voltage must add up to what? To the amount that is being delivered. Is that okay? So now let's go to number 2. Number 2 says 2 capacitors of 6 microfarad and 8 microfarad are connected. Now, the question might give you in microfarad and give you options in millifarad, or even give you options in farad. You know how to convert already, right? Okay. So 2 capacitors of C, 6 microfarad and 8 microfarad are connected in series. So if they are connected in series, it means that the equivalent capacitance will be equal to 1 over 6 plus 1 over 8. Let's see what we have to do first. What additional capacitance must be connected in series with this combination to give a total of 3 microfarad? So what must you connect here to give you plus 1 over x in series? Does that make sense? To give you 3. Will it be 1 over 3 or 3? To give you the capacitance there is 1 over it to be 1 over 3 too. Do you get it?
Yes, sir.
To be 1 over 3. Do you understand?
Yes, sir.
You know the equivalent capacitance is still 1 over 3 here. So we now have this guy, LCM of this guy and this guy, 24 x, right? 24x. 6 in this guy, 4. 4 by 1, 4x. I mean, x, that's the point, right? 4x. 8 in this guy, 3x plus times this guy, 3x plus x in this guy, 24 times 1, 24 is equal to 1 over 3. So what do we have here? We have this plus this, 7x plus 24 over 24x is equal to 1 over 3. By the time you cross multiply, you have 24x is equal to 3 times this, 21x plus 3 times this, 72. This one will come here, we have 24x minus 21x is equal to 72. So we have 3x is equal to 72. And x is equal to what? 72 divided by 3 is what? 24. 24 millifarad. So that's the answer here. Let's go to number 3. Number 3 there says, so it says this system is connected like this. So we have this. We have now, which ones are in series, which ones are in parallel? These two are in series, right? But the best bet is this. Let me show you the fastest way to do it. Do these two together first, that are in parallel, and do the rest do everything in series. Is that okay?
Yes, sir.
So when you resolve this part, you get C will be equal to 2 plus 4 equals 6 millifarad. So you now get that 1 over C will be equal to 1 over 2 plus 1 over 3 plus 1 over 6 plus 1 over 4. So LCM again is 12. 2 here, 6 plus 4 plus 2 plus 3. This becomes 10, 12, 15. 15 over 12, 3, 5, 4. So 1 over C is equal to 5 over 4. So C equals what? 4 over 5 microfarad. Yes. 0.8. If the force, yeah. The next one says, if the force on a charge of that Coulomb, so the charge is what? 0.2 Coulomb. In an electric field is 4 Newton. The force on it is 4 Newton. Then the electric field intensity of the field is what? So E is what? Recall that E is F per Q. So this becomes 4 over 0.2 equals to 20. So E equals what? 20 newtons per coulomb. Then number 5. Find the work done in moving a 2 coulomb charge between 2 points X and Y. Find the work done, W, in moving a 2 coulomb charge. You see the way I'm writing what I'm given?
Yes, sir.
2 coulomb charge between point X and Y. And if PD is 100 dagger, V is what? 100 volts. So we come here and recall that V equal to W per Q. So that W will be equal to what? QV. Does this make sense? So that W therefore will be equal to W equal to what? 2 times 100. That becomes 200 joules. Are we clear? So we are good with this. Number 6. If 8 that guy work is done, so work that is done is 8 times 10 to the power minus 2 joules. Is required to move that amount of charge. So Q is 100 microcoulomb from a point X to a point Y in an electrical circuit. The PD between X and Y is what? Very simple, right? W will be equal to QV, so that V equal to W over Q. That will equal to 8 times 10 to the power minus 2 over 100. Is that okay? No?
100 times 10 to the power minus 3.
Minus, no. This one will come down.
Yes,
Minus 2 was what we had before now. Okay. So that it becomes 8 times 10 to the power minus 2 times 10 to the power minus 2. How does it change to minus 6? Oh, okay. I'm sorry, thank you. So times 10 to the power minus 6. So then times 10 to the power 6 here. Once it comes up. You understand what I did?
yes, sir.
You know here it will become, this thing should become 8 times 10 to the power minus 2 times 10 to the power minus 6. Because it's division. Okay. So now it becomes 8 times 10 to the power minus 4 plus 6. 8 times 10 to the power 2, right?
Yes, sir.
Volts. Okay. Number 7. We have this. So we should find the resultant capacitance. So which ones are in series and which ones are in parallel? So 1 and 5 parallel. So if we resolve it in parallel, then the entire thing will not be in, because this is a junction here. There are 4 junctions here. 1, 2, 3, 4. So let's do that. So in parallel, let's call this one C1. If you're doing WAEC, you know you have to label all these things and be explicit. So C will be equal to C1 plus C2. That is what? 1 plus 5. That will be 6 mil farad. So our circuit has now become this, and this, with the 2 junctions here. So this is what? Series, isn't it? So we now have 1 over 4, or you say 1 over C will be equal to 1 over 4 plus 1 over 6 plus 1 over 4. 1 over 4 plus 1 over 4 equals 1 over 2. 1 over C equals 1 over 2 plus 1 over 6. The LCM is 6. 2 in 6, 3 by 1. 3 plus 6 in 6, 1 by 1. That's 4 over 6 equals 1 over C, right? You invert this, becomes C, means you invert this too. 6 over 4. 2 here, 2, 2 here, 3. This C equals what? 1.5 mil farad. So then, for number 8, we have that guy, that system, and so we should determine the PD across only this guy, only the 5 mil farad guy. But we know that as this guy is like this now. So in this system, since it's only this guy we are targeting, we only need to resolve these two, because they are the only ones, having something to do with each other. You get what I'm saying? So if I resolve this, I'm going to have, they are in series. So I have 1 over C will be equal to 1 over 5 plus 1 over 15. LCM is 15. 5 and 15, 3 by 1, 3 plus 5 and 5 times 1. So we have 4 over 15. So that C will be equal to what? 15 over 4 now. This is the equivalent capacitance there. But what is the charge flowing? Is that okay? So since they are in series, the same charge will flow through here. Exactly. Once they are in series, what will happen? Some charge will flow through here. So let's see the charge that's flowing through them. Since C equal to Q over V, right? So C will now be equal to, we are looking for charge. So charge will equal to CV. So what is C? 15 over 4. Q will be equal to 15 over 4 times V. V is 24. V is 24, right? Here 1, here 6. 6 times this. 4 times this is 60 plus 30, 90. 90 mil per charge, right? Mil Coulomb. 90, really mil, since that guy is mil, so it will be mil too, right? So mil Coulomb now, charge is Coulomb. Are we good? So this is the 90 Coulomb that flow across who and who? Good. So we now want to get the potential difference across only 5. So potential difference is equal to charge that is flowing through capacitance. So that will be V will be equal to, what is the charge flowing through? 90 mil Coulomb over 5. Here 1, here 16, 17, 18. So V equal to 18 volts. Are we clear?
Yes, sir.
Is it hard?
Yes, sir.
Okay, so let's solve the remaining 2. And what's the time? This is what we'll do. After this set of questions, we'll go to the next field. What's the next field? We are seeing electric field. You know it's still much. So let's finish electric field there. And let's finish electric field. We'll take some more questions. If there's now time later, we'll now take for more and more questions. Are we good?
Yes, sir.
The capacitance of a parallel plate capacitor when air is in the presence of air. Is that okay? In air, that is when the air is the dielectric. Air is this one separating them. So the capacitance is 3 microfarad. And in the presence of the dielectric material, 6 microfarad. So this is C when it is air, C when it is dielectric material. So that becomes what? 6 microfarad. So it now says the dielectric constant. So the dielectric constant is going to be, just take the ratio of the material to that of air. Is that okay?
Yes, sir.
So that becomes, air is not free space. Vacuum is free space. Is that okay? So the dielectric constant, what do we use for that now? Let's write it as dielectric constant is going to be equal to what? C sub m over C sub a to be 6 over 3. And that's what? 2. It has no unit. Is that okay?
Yes, sir.
Of course, they even said it's constant. So the energy stored in a capacitor of capacitance, that capacitance is 10 mil microcoulomb, carrying a charge of 100 mil coulomb. This was a mil farad. Capacitance is in farad now. Mil farad, and the charge is 100 mil coulomb. Is what? What's the energy stored? Formula for energy stored: half CV squared. And C is equal to Q over V. So that V will be equal to Q over C. Does this make sense? So you can replace that by that. We have E will be equal to half C times V will be Q over C all squared. You cancel this, which means 1 here, right? Are you with me? E will be equal to half times Q squared over C. Am I correct or wrong?
Correct, sir.
So that will be equal to Q squared 100 times 100 times 10 to the power minus 6 all over, 10 to the power minus 6 twice. Does that make sense? This becomes 100 times 10 to the power minus 6 all squared over 2 times C, 2 times 10 times 10 to the power minus 6. So here, this one will take care of 1, right? 10 here 1, and here 5. So we have E will go to 5 times 10 to the power minus 6 joules. Are we good? All right, so let's go to the next field. What is the next? Okay, no. The next segment of electric field, that is current electricity. That is what? Okay. So we are going to be starting with what is known as the direct. All right. So far we have discussed the concept of electrostatics, which refers to charges at rest. But now we are going to be talking about charges that are moving. Is that okay? So the rate of flow of charge is called what? Current, and it is denoted by I. You say the rate current is the rate of flow of charge. Is that okay? Now there are two types of currents. We have the what? What are the two types of currents? Direct current and alternating current. So first, let's discuss the direct current circuit. And in a direct current circuit, what happens is this. We call it direct current because the path of current is unidirectional. The path of current is what? So with that, we give rise to different types of circuits. We have about 3 types of circuits. A circuit is basically a connection of electrical components where current is allowed to pass. Is that okay? The circuit is just the path through which current flows. Circuit is what? And of course, we mean that. So you already know that it will be wires basically that will be there, conductors throughout. Okay. First, let's talk about electrical components. Let's talk about electrical components. Now, if you see this, what comes to your mind? If you see this, what is this? This is a cell. Good. If you see this, battery, right? Because we say battery is an aggregation of cells, right? Okay. If you see something like this, capacitor. If you see something like this, the switch or key. Okay. What if you see something like this? This is a two-way switch. This is what? Okay. What if we have something like this? A junction, right? Wires are joined. So, what if we have something like this? Okay, let's talk about the other ones. What does it represent? A voltmeter. What does it represent? What does this represent? This one? Galvanometer. Is that you see this way or you see this way? Is that okay? And we said we can always convert a galvanometer to both an ammeter and a voltmeter. So, what of this guy? What if you see something like this? Earth, good. Alright, what if you see something like this? So this is Earth. What if you see something like this? A diode, right? What if you see something like this? Resistor now. What about this? Huh? Which one is resistor? Both of them. What kind of resistor is this? A constant resistor. A what?
Constant resistor.
How about you now have something like this? A rheostat or a varying resistor. Is that okay? Varying resistor. So what if you now have something like this? Something like this. Something like this. What do we have this guy? LED. A light emitting diode. What if you have something like this? Which other one? Inductor. What if you have something like this? I'm forgetting how to draw it, but I think it's something around. Which one represents transformer? Something like this, right? A coil. Yes, that's what I'm saying. Yeah. Right? So this is a transformer. Is that okay? Do you get it? This one? Inductor. How about this? Are you with me? How about this? Alternating current voltage. This is alternating voltage actually. This is what? So, and of course, it produces alternating current. So, we're still going there today, right? In this video, right? Alright. So, now let's talk about types of circuits. There are three types of circuits. We have the what? The what? Open circuit. Now, closed and what? Short. So, an open circuit is one in which what? Is open, so current is not okay. How about this? A closed circuit is one in which what? Huh? Good. Key is closed, current is flowing. In what direction here? Rightward or leftward? Rightward or leftward? Rightward, right? That's the leftward. From left to right. Good. How about a short circuit? What's a short circuit? Is one in which what? Okay, now look at this. Look at this, look at this. So this will be our load. This is the source. Let this be the load here. Let's put the load here. Huh? What is it? What is it? Yes, we didn't put a load, right? Alright, look here. So now in this one, this looks like a closed circuit, right?
Yes, sir.
Now, but what do I do like this?
Short circuit.
This is now a short circuit. Do you know what I've done? Why is it short? The load has been bypassed. Wire has been used to bypass the load. So this connection has provided another path for flow of current. So if current was flowing from positive to negative normally, which is normally, what will happen is that it will decide, nobody likes work. Is that okay? Current guys, they are lazy. So current will just, rather than flow to the load, will flow past freeway. Do you understand now?
Yes, sir.
So because of that, if this was a bulb, for example, a resistor bulb, it will not on light. Do you get it?
Yes, sir.
So this is what?
A short circuit.
All right. Good. Now, we have two types of cells basically. We have the electrochemical cell and the electrolytic cell. This one so far that I've been talking about, I've been using here, is an electrochemical cell. All right. Now, a battery, how a battery is created. I'll link the video in the description where we talked more about it. But basically, an electrochemical cell, you are most likely to be tested on the problem or disadvantage of electrochemical cell. What is that? Smell. Cause it. Cause it. Okay. So that's short circuit. I said electrochemical cell is a cell that converts chemical action into what? Electrical energy. So it converts chemical energy to electrical energy. So basically, the idea is that the reverse of what is going on here is what is going on in the outside circuit. Is that okay?
Yes, sir.
Usually they ask you the problems associated with cells. And there are two major problems. What are they? Polarization and what? Local action. Polarization and what?
Local action.
Should I quickly take you through it?
Yes, sir.
Basically, this is what you see in an electrochemical cell. So you could have our electrolyte. So in this case, let's use H2SO4 as our electrolyte. Is that okay? Are you with me?
Yes, sir.
Then one of these plates will be zinc plate, the other will be copper plate.
Yes, sir.
So now you connect wire. You connect a load to it like a bulb. What you notice is that the bulb begins to glow. Is there any source of power here? No. The source of power here is that there is difference in electrode potential here. Is that okay?
Yes, sir.
The electrode potential of this guy, which one is higher? Let's see. The electrode potential is the capacity of a particular metal to do what? To draw electron. Do you understand?
Yes, sir.
So which one will be more likely to draw electron? Is it a metal that is higher in the series or a metal that is lower in series? That is lower in the series. Does that make sense? So that's why we have zinc. Let's draw the electrochemical series. Give it to me.
Potassium.
Mm-hmm.
CA,
Mm-hmm.
Mg,
Mm-hmm.
L,
Mm-hmm.
Zn,
Mm-hmm.
Fe,
Mm-hmm.
Sn,
Mm-hmm.
Pp,
Mm-hmm.
H, Cu,
Mm-hmm.
Hg,
Mm-hmm.
Ag,
Mm-hmm.
Au.
Platinum should be here. Anyways, if until now, don't lie, if you have not known this electrochemical series, raise your hand. Don't lie, I'm not using it against you.
I just don't know it now.
You don't know it in this. Alright, so the guys that are higher here will have low electrode potential. The guys that are lower will have what? High electrode potential. So remember, if I remember vividly when I was teaching you this, I told you that the electrode potential of this cell is going to be what? Positive. Do you remember? But the Gibbs free energy of this cell is going to be what? Negative. Why? For a negative gives free energy, what else? What does it tell us? It's spontaneous reaction. So the moment you connect this wire, electron begins to flow. That's spontaneous. So, but the electric potential is positive. For electrolytic cell, the electric potential is good. And the gate change in gauge free is what? Positive. Does that make sense? Non-spontaneous. Why? Because you know that we needed to connect a battery first before current began to flow on that day in that thing. Is that okay? So it needs an energy source. So it's non-spontaneous. So Gibbs free energy is positive. If Gibbs free energy is negative, what do you call that reaction? Gibbs free energy is zero, rather. If Gibbs free energy is zero. If change in Gibbs free energy is zero, the reaction is in equilibrium. The reaction is what?
In equilibrium.
But if Gibbs free energy is negative, in that case, the electric potential of that chemical reaction will be what? Positive. And in that case, we'll call that kind of reaction what? Spontaneous or feasible. Spontaneous or what?
Feasible.
A feasible reaction is a spontaneous reaction that happens on its own. Is that okay?
Yes, sir.
Then if Gibbs free energy is positive, the reaction will be called what? Non-spontaneous and what?
Non-feasible.
Non-feasible. And the electric potential will be if the change in Gibbs free energy is positive, the electric potential will be what?
Negative.
Good. If the Gibbs free energy is negative, the electric potential will be what?
Positive.
Okay. Okay. Anybody asked me if the E cell is zero, what will happen? Let me ask you that. If the E cell is zero, is what? What will happen? Equilibrium. No reaction will take place. Is that okay?
Yes, sir.
That makes sense too. That makes sense. So in this guy, where will electron flow from? From who to who will electron flow? Electron will flow from zinc to what? Because copper has a higher pull on electron because it's lower in the series. Is that okay?
Yes.
Copper has a higher pull on electron, so it will be pulling electron from zinc to itself. How many electrons will it be pulling to itself? One actually, one copper will take, but one copper takes 2 electrons. Is that okay? So electrons will start moving here, and since the electron begins to move, that's electricity being generated. Okay, so as the electrons are moving here, then electricity is being generated, and so where will the anode be, and where will the cathode be? Which one will be the anode? These are electrodes, right? These are our electrolytes H2SO4. Which one will be our cathode? Which one will be our anode? What is a cathode? A cathode is a negative electrode. An anode is a positive electrode. Is that okay? Now, in this case, which one will be our anode here? If this guy is positive, it means current is flowing from him, right? So zinc will be our, does that make sense? Copper will be our cathode. So what now happens is this, that this guy, each of these guys will be getting reduced, right? Gain of electron reduction, right? So Cu2 plus will be gaining 2E minus will become what? Copper elite. There's a copper atom. Is that okay?
Yes, sir.
Alright, this is just the half cell reaction. Then the second half cell, the anodic half cell, what? Zinc will give zinc 2 plus 2E minus. Is this clear?
Yes, sir.
I've told you the other way to write this thing is like this. Since zinc is the one giving out the electron, so zinc is losing electron to become zinc 2 plus ion, right?
Yes,
So you now bring this guy to that side. This becomes zinc to become zinc 2 plus plus 2e minus. Okay. Now what is now polarization? This is polarization. Polarization of cell. This is one of the defects. There are two types of cell. There are primary cell and secondary cell. So this is a primary cell we just gave now. This is a voltaic cell. This is a what?
voltaic cell.
Or galvanic cell. Now this voltaic cell has one problem, which is polarization. And that polarization is due to the fact that H plus will be attracted to what way? You know, here we have H plus and SO4 2 minus. Where will SO4 2 minus go? They will go to the anode, and this one will go to the cathode. So what will now happen is this, that there will be another EMF set up between this one and this one. There will be exchange of electron again between this guy and this guy. And because of that, because bubbles of H hydrogen will be formed there, is that okay? So there will be what is called back EMF. So that direction of flow is supposed to be this, then there will be a back EMF in the other direction. Is that okay?
Yes, sir.
And so because of that, back EMF causes this thing to run for a very short while. To stop running after a very short while. Is that okay?
Yes, sir.
So that is called polarization when there's back EMF. Remember I've talked about back EMF in, where did we talk about back EMF? Electromagnetic induction. We'll still get there today. Okay. So then the second thing is local action. That's the second thing is simple cells, primary cells. Local action is just after the system has stopped running, you disconnect the wire. If you leave this guy like this, some deposit of maybe not even deposit, as it is, if you remove this wire, there are impurities in some of these metals. Is that okay? They will create another system of exchange of ion. Do you understand? Do you get it? So impurities might, for example, if there is a metallic impurity here in this zinc, to create another system of another circuit will be created inside it. Do you understand? Okay, so that's local action. So and because of local action, there is depletion of what? These metals, and because of that, the system will not run for long. Is that okay?
Yes, sir.
So now, these guys have more advantage over them, secondary cells. Now this is how to remember. Which ones are primary cells? Primary cells are the ones that they cannot be recharged after use. Primary cells cannot what?
Recharge after use.
But secondary cells
Can be recharged
after use. So they could ask which of these can be recharged after use. First, primary cells are the ones that contain name of people. That's just how to remember it. You hear Daniel cell, what kind of cell is that?
Daniel cell. Primary cell.
If you hear Leclanche cell, what kind of cell is that?
Primary cell.
If you hear who cell again?
Martin cell.
Martin cell.
Daniel.
Please, Daniel cell, thank you. Leclanche cell. Clanche, I didn't spell it well. This is not there. Is it not French? And you've never seen it before.
I've seen this name.
Okay. So do you know that this is also here? Okay. All right, let's go, please. Then if you, for secondary cell, if you now hear anything like nickel cadmium, silver cadmium, anything, although when they mention metal together, that will be what? Secondary cell. Okay. So you've not seen it in Lichatelia's name too. Oh, what do you know? Okay, now, so let's get to our normal circuit now. So in a circuit, there are the various components. We have voltage, we have the resistor or resistance, and we have what? Current. So current, let's have voltage. Let's have voltage. Current is high. So there is something called the Ohm's law. Now, Ohm's law, you can use the formula triangle to remember it. Ohm's law is given like this. Voltage is equal to what? IR. What does it say? It says the potential difference across the two ends of a metallic conductor is directly proportional. The current flowing through a metallic conductor is directly proportional to the potential difference across its end. Is that okay?
Yes,
or the voltage or the potential difference between two ends of a metallic conductor is directly proportional to the current flowing through it, provided that physical quantities like temperature, etc. are kept constant. So for ohmic conductors, when you pass a current into them, what you get is as you increase your voltage, what will be happening to the current? It will be increasing. All right. So, but the point is this: the resistance too might. What does the resistance do? It impedes, or we say resistance is the opposition to the flow of current. Now, resistance resists the flow of current, and is a passive component. Is that okay? What it does is it doesn't use up energy. What does it do to the energy? It converts it to what? To heat energy. Okay, so let's go over voltage. Now, if you come, so what is the appropriate way to connect voltage sources? What's the appropriate way? Is it in series or in parallel? In series. Is that okay?
Yes, sir.
So just like your battery at home, if you want to connect to the system, you know you put a battery here, the next battery in front, next battery in front. That's series. Is that okay?
Yes, sir.
Then for now, because voltage is a good component, is that okay? Because it provides energy. So let's go through a simple circuit now. If I have this, and I give it a particular amount of voltage, let's say I give it 12 volts of energy, I supply it into the system, and my switch is closed. What will happen? Current will begin to run. Current will begin to run in this direction, right?
Yes, sir.
So as electrons flow in this, well, which direction does the electron flow?
From positive to negative, from negative to positive.
Conventional current.
Conventional currents flow from positive to negative. Electrons flow from negative to positive. Is that okay? And because in electricity, we decide that it is positive charges that are moving. So if positive charges are moving in this direction, it means it makes sense to say that negative charges are moving in the opposite direction. Does that make sense?
Yes, sir.
All right, so that's why it works. So we use it.
Sir.
Now we have, so this voltage is going to run through here. I mean, this voltage is going to drive current to move through here. So as charges move through here, what will happen? The charges will lose energy, right?
Yes, sir.
So then flow back and take up another energy and continue to move like that. Is that okay?
Yes, sir.
Until this guy begins to heat up because it is converting the energy to heat. Okay? So now we also know that so what other thing do we need to talk about? So voltage in series, right? Voltage in series is the correct guy. But voltage in parallel, if you connect voltage in parallel, what will happen? If I connect this, so what now? If I connect this, number one, now, you know that this voltage, there are three cells here.
Yes, sir.
In these three cells, for you to connect them, number one, they must be of equal voltage. Is that okay?
Yes, sir.
If not, current will not run. Do you get it?
Yes, Yes, sir.
So now that they are equal, so what if I say this one is 15 volts, 15 volts, 15 volts? If I say what's the amount of voltage in this circuit, let's say there's a circuit that continues like that. What's the total amount of voltage in this circuit?
15, sir.
15 volts. Does that make sense?
Yes, sir.
If I had connected them like this, we use dot 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 actually to show that they are always touching. It's not wire. Do you understand?
Yes, sir.
As in when we draw line is wire, when we use dot dot dot, it means they are touching. And this way you connect it. Positive of one to the negative, negative of one to the positive of the other, negative to the positive. Is that okay?
Okay, sir.
Now in this case, we have 15 volts, 15 volts, 15 volts,
45.
45 volts. Good. And this makes sense again because I remember I told you that for this guy,
Yes.
capacitance is directly proportional to capacitance is equal to Q over V, right?
Yes, sir.
There's inverse proportionality.
Yes, sir.
So the series of this one will be just add it up.
Yes.
The series of this one will be take the inverse. You understand now?
Yes, sir.
Okay. So now let's talk about resistors in parallel and resistors in series. You're most likely to see this. Now, resistor